Hello students, in today's presentation we shall see hierarchical clustering. I have already given a gist about hierarchical clustering I think in my previous presentation, but just let's look into it once again. Hierarchical clustering creates a hierarchical decomposition of a given set of data objects. There are two types of hierarchical clustering. One is agglomerative and another is divisive approach. In our agglomerative approach is also called as bottom-up approach. That's because we start from the individual data objects and then we find the similarity between the two different data objects and we form a cluster, and then once again we go on finding the similarity between the cluster and the other data objects, and then we find one more level, upper level of cluster, and likewise we go on doing it. A best way of explaining is through this example where PQRST are individual data objects. We find the similarity of these objects with one another and we come to a conclusion that okay, P and Q are more similar. Here S and T are more similar, and then we once again find the similarity of this cluster with the rest of the data objects or rest of the clusters, and we find that okay, R, S, T are more similar. We form that cluster, and then finally we get the overall cluster here. And if you go from bottom to up, it is said to be agglomerative, and if I come from top to bottom, it is said to be a divisive approach. Now, a real-time example of such hierarchical clustering is one such example is animal kingdom. If I consider various fishes or various reptiles or various amphibians, mammals, worms, insects, and crustaceans, then all of these form the individual data objects. All of the fishes will have a common characteristics, and that's why they form a cluster. All of the reptiles will have a common characteristics, and that's why they form a cluster of reptiles. And similarly with the other animals. Now, all fishes, reptiles, amphibians, and mammals have some common characteristics, and that's why they form a cluster that is vertebrate. And all worms, insect, and crustaceans have one common characteristics, and that's why they form invertebrate cluster. And both of these form a common cluster, which is called as a animal cluster. So you may find many such examples wherein you can form subclusters, and from that cluster you can once again combine with some other cluster in order to get the main cluster. Now, in between, there's one more small concept that has to be covered, which is called as dendrograms. Dendrograms are nothing but the pictorial representation of hierarchical clustering. Now, this one, what you can see here is a dendrogram, which says that A and B are similar. So every root here shows a cluster. CD is a cluster. CD along with E forms a cluster. AB along with CDE forms a cluster, and ABCDE along with F forms another cluster. So here you can actually represent on the y-axis here, you can represent the similarity between A, B. So x-axis represents the data objects in itself, and y-axis represents the similarity measure, the similarity at which A and B have formed the cluster. So a dendrogram is a tree-like structure which represents hierarchical technique. Leaf node, individual objects represents the leaf node, and every root node represents a cluster. A cluster at level 1 is the merger of its child cluster at level I plus 1. So there are three main techniques under hierarchical agglomerative clustering. The first one is a single nearest distance or single linkage. In this type of clustering, we find the distance between the closest members of the two clusters. in this type of technique, we find the closest members, the distance between the closest members of the two clusters. The next technique is a complete farthest distance or complete linkage, in which we find the distance between the members that are farthest apart. And the last one is the average distance or average linkage, in which method we find the distance between all pairs and averages of all these distances. The concept will be more clear to you when we take up an example. Yeah, so this slide has an example on single linkage cluster. That is the first method, wherein we find the distance between the closest members of the two clusters. So the question says, find the clusters using single link technique, use Euclidean distance and draw the dendrogram. So in the question, a data set like this will be given to you, wherein in this question you have P1 to P6. There are 6 data objects and there are 2 dimensions, X and Y. And this represents the pictorial or the graph, the scatter plot of the same data set. The scatter plot of the same data set. Now what we have to do is, we have to find the distance between every two objects. So we have to find the Euclidean distance between every pair of objects. So I have shown you here how you compute the distance between the first two objects, that is P1 and P2. So by the application of Euclidean distance between P1 and P2, I get a distance of 0.23. Likewise, I have to find distance between P1, P3, P1, P4, P1, P5, P1, P6, and P2 to P6, P3, P4. Like every pair of data objects, you have to find the distance, and finally you will get a distance matrix, something like this. The distance between P1 and P2 is represented with 0.23. Distance between P1, P3 is represented as 0.22. So likewise, you have to find distance between every pair of objects. Once you do this, I have to cluster the objects. So in order to cluster the objects, I should find those two objects which are quite similar to one another, or the dissimilarity is minimum, or the distance between the two objects have to be minimum. Only then I can say that they have a very high similarity. So when I go through this, I find that 0.11, yes, 0.11 is the smallest distance among all the distances that have been listed out here. So 0.11 is the smallest distance. So what I can do here is that I can merge P3 and P6. So 0.11 is between P3, is a distance between P3 and P6, which is the smallest. So these two data objects are very similar. That means that I can merge these two objects. So P3 and P6 have been merged, and a small dendrogram is shown here between P3 and P6 object. Now when I do this, in the next step, my distance matrix is going to get changed like this. Now P3 is no more P3, it is P3, P6. So P3, P6 here, and here also it is P3, P6. So I have P1, P2, P3 is no more P3, it is clubbed with the P6. So P3, P6, P4 and P5 remains as it is. So what happens here is that from this matrix, I have P1 to P2 as 0.24. But how about P1 to P3, P6? I don't have a distance as such. So what is going to be there in that particular box? We shall see that. Next is P1 to P4. Okay, I have the value here, that is 0.36. P1 to P5. Okay, I have the value here 0.23. Likewise, I have all other values except for I have P3, P6, for which P3, P6, P4 I don't have a value, and P3, P6, P5 ones also I don't have a value. So all these question marks have to be filled with some value. Now let us see what value we have to fill. Now if I see P1 to P3, P6. Now, what is the distance from P1 to P3? Here, P1 to P3 is 0.22. P1 to P3 is 0.22. And then I have P1 to P6. P1 to P6 is 0.23. So P1 to P3 is 0.22. P1 to P6 is 0.23. Now, which among these two values is small, whether 0.22 or 0.23? So 0.22 is smaller. We are going to combine the most similar items together, so I have to be considering the minimum value. So in this column, I'm going to consider 0.22 as the value. I should be getting the minimum of P1 to P3 distance and P1 to P6 distance. Next is P2 to P3, P6. So I should be finding whether P2 to P3 is smaller or P2 to P6 is smaller. Now P2 to P3, P2 to P3 is 0.15, whereas P2 to P6 is 0.25. So 0.15 is smaller, so I fill that box with 0.15. Next, P3, P6 to P4. So P3, P6 to P4. So first I should be finding whether P3 to P4. P3 to P4 is 0.15 and P6 to P4. P6 to P4 is 0.22. So 0.15 is smaller here. So I fill that value with that 0.15. Next, P5 to P3, P6. Check whether P3 to P5 is smaller. P3 to P5 is 0.28. P6 to P5. P6 to P5. 0.39. So it is 0.28 and 0.39. 0.28 is smaller, so fill that question mark with the 0.28. So the same description is given here, and I have given the explanation only for, I think, only for two boxes here. The rest of the two boxes are also solved in the same way. We are going to find the minimum distance between the pair of objects. So once I do this, next I have to be finding which is the next so one iteration is done here. Now from this distance matrix, once again I should find out which is the smallest value. So the next smallest value is 0.14. So yes, here I have the smallest value, that is 0.14 between P2 to P5. So P2 and P5 are clustered here. So the dendrogram here, it says P2 to P5, which merges at a value of a 0.14. 0.14, and earlier P3, P6 merged at 0.11, which is shown here. So this is slightly smaller in height when compared to P2. So this is at 0.11 and this is at 0.14. So I merge, so 0.14 is the smallest, so I can merge P2, P5. So I have P1, P2 is no more P2, it is clubbed with the P5. So P2, P5, P3, P6 I had already clubbed in the previous iteration. Next coming to P4 and similarly here along the row. Now P1 to P3, P6, I already know the value. P1 to P3, P6 is 0.22. P1 to P4 is 0.37. Then what else I have? I have, yeah, P3, P6 to P4. P3, P6 to P4, I have 0.14. So how about the rest of the values there? It's a question mark. So I should be finding now whether P1 to P2 is smaller or P1 to P5 is smaller. So P1 to P2 is 0.23, P1 to P5 is 0.34. So 0.23 is smaller there. So this value is filled with the 0.23, as you can see here, 0.23. Next, coming to this value here. Yeah. So P2 to P5, and I have P3, P6 here. Yeah. So P3, P6 to P2. P3, P6 to P2 is smaller or P3, P6 to P5 is smaller. So P3, P6 to P2 is 0.15 and P3, P6 to P5 is 0.28. So 0.15 is smaller there. I hope it is understood. My P3, P6 I already have here. So I should be finding the distance of P3, P6 to P2. P3, P6 to P2 that is 0.15 and P3, P6 to P5. P3, P6 to P5 that is 0.28. So the smaller value here is 0.15. So I merge it and I get 0.15. And then how do I do this? Whether this question mark here, whether P2 is near to closer to P4. P2, P4 is P2, P4 is 0.20 and P5, P2 is 0.14. So 0.14 is smaller. So sorry, P4, P2, P4, P2 is 0.20 and then I have P4 and P5 that is 0.29. So 0.20 is smaller, so it is replaced with 0.20. So once I get this, I should be finding the next minimal value among these value, which is nothing but 0.15, which says that, okay, I can combine P2, P5 and P3, P6. So P2, P5 and P3, P6 is once again put under one more cluster, and this is how the box looks like, the distance matrix looks like. So P1 is 0, this to this is 0, P4 to P4 is 0. I already have P1 to P4 distance, that is 0.37, which I've put here. But what right now I don't know is the distance between P1 to this cluster, that is P2, P5, P3, P6, and the distance of P4 to this cluster, that is P2, P5, P3, P6. So what do I do now? Whether P1 is closer to P2, P5. P2, P5. P1 is 0.23 and P1 to P3, P6 is 0.22. So 0.22 is smaller. So I replace this with 0.22 here, right? And then yes, I have to check whether P4 is closer to P2, P5. P4 is closer to P2, P5, that is 0.20, or P4 is closer to P3, P6, that is 0.15. So yeah, it is the same. So anyways, that's going to be 0.15 itself. Next, once again, I have to see which among these is smaller. So 0.15 is smaller. So I can combine. Yes. So what I've done here is that I have combined P4 with this cluster, and I have shown it here. And what should come here? I have to be seeing whether P1 is closer to P4. P1 to P4 is 0.37. P1 to P4 is 0.37, or whether P1 is closer to P2, P5. P1 is closer to this one, so that is 0.22. So 0.22 is smaller. So I replace here this one with 0.22, and finally P1 will get merged with this. So this is how the finally we started with P3, P6, and then we combined the P2, P4, and then we combined, I think we combined P3, 6, P2, 5, and then we combined P4, and then finally P1. And this how the dendrograms looks like. I repeat once again. The values on the y-axis are going to be the individual data objects, whereas the values on the y-axis are the similarity measures at which the data objects get clustered. So this is how the single linkage cluster of hierarchical agglomerative clustering works. Yeah, thank you very much.